When Michio Kaku finally addressed the latest revelations from the James Webb Space Telescope, the scientific world held its collective breath. For weeks, astronomers, cosmologists, and theorists had been fixated on a single image, a distant patch of deep space captured in unprecedented detail, one that appeared beautiful at first glance but carried with it implications so enormous they threatened to upend our entire understanding of the universe. Early on, it looked like just another far-off galaxy, glimmering dimly in the distant edge of infrared space. But as information flooded in and numbers were double-checked, it became apparent this wasn't just another leap in astronomy, it was a seismic shift. Michio Kaku, one of the world's best-known physicists and string theory pioneer, had been quiet amidst the growing hype. Revered for his capacity to explain the most abstract reaches of physics in terms the layman can understand, Kaku's silence was unprecedented. Researchers everywhere held their breath. What could he possibly say about a galaxy that, by all conventional cosmological measures, does not even deserve to be? When at last he broke his silence, the impact was charged. He did not merely remark upon the picture, he provided a theoretical framework that recast the whole discovery, transforming what appeared to be a vexing anomaly into the portal to a fresh vision of the universe. The photograph that brought about this disruption depicted a galaxy, venerable, enormous, and unsettlingly organized. It was so far out that the light it emitted had taken over 13.5 billion years to reach the telescope, making the object's origin a scant few hundred million years after the Big Bang. But it wasn't the galaxy's age or distance that surprised scientists. It was how it appeared. It did not look anything like the irregular, disheveled galactic pieces that modern simulations suggest would have developed during that initial period. Rather, this object exhibited the unmistakable signs of adulthood: clean, well-developed spiral arms, a compact central stellar bulge, and even suggestions of ordered star populations and dust lanes, all elements that had been thought to take billions of years to develop. This went against the lambda cold dark matter, lambda CDM, model's predictions, which has been the accepted model of the universe's large-scale structure for a very long time. The model predicts that the earliest galaxies in the universe were small, clumpy, and unstructured, not at all like the magnificent spirals we observe today. The creation of complex galaxies, the model maintains, is a hierarchical and slow process, starting with small objects colliding over long periods. But here was an image, a stark, beautifully rendered image, that appeared to leap over that whole process. Kaku's reaction to this seeming chronological anomaly was both sound and provocative. He cast the discovery not as a glitch in observation or an anomaly in the data, but as a potentially revolutionary moment in physics. With his usual combination of imagination and scientific discipline, he speculated that we could be glimpsing the boundaries of our present models and perhaps, indeed, the boundaries of our conception of time and space itself. What if, he wondered, the laws we think govern the early universe are incomplete, or better yet, fundamentally incorrect? What if this galaxy's unlikely evolution wasn't merely an aberration, but a message from the universe nudging us toward greater understanding? One path of investigation he pursued was the possibility of entirely new physics at work in the early stages of cosmic history. The conventional narrative of the universe's origin and evolution depends on cosmic inflation, a fleeting period of exponential growth that stretched space itself and set up all subsequent structure. Subsequent came the cooling, the gravitational coalescence of matter, and the gradual appearance of stars and galaxies. But suppose, Kaku proposed, there were unseen forces at play. Exotic particles or unidentified types of dark energy or radiation that accelerated galaxy formation much more quickly than we ever imagined. Maybe dark matter doesn't simply influence galaxies passively through gravity. Maybe it possesses or undergoes as yet unknown properties or interactions that, with the right circumstances, could accelerate the grouping of matter into large systems. Or perhaps the cosmological principle itself, whether the universe is homogeneous and isotropic on a large scale, must be questioned. What if some areas of the universe develop differently? What if spatial variations exist, hotspots of accelerated growth because of external conditions or even effects from other dimensions? These were not fantasies uttered for the sheer sake of imagination. Kaku rooted his ideas in decades of work on string theory and higher dimensional physics. He talked about the prospect that what we see could be an interaction between our universe and another, perhaps a neighboring brain in a higher dimensional multiverse. In such a scheme, the universe that we know lives on a three-dimensional membrane suspended in a higher dimensional space, and under special circumstances, energy or matter could leak across the brain boundaries. Such a phenomenon might, in theory, impart sufficient energy into our universe to cause the early formation of structure in remote areas, leading to galaxies centuries ahead of their time. He stressed that we need to recall, science doesn't advance by putting each new observation into neat theory boxes. Science advances when observations push us to challenge the theories themselves. Each revolutionary advance in physics, Newton's laws, Einstein's relativity, quantum mechanics, has come not from comfort, but from contradiction. And this finding, Kaku said, could be the first crack in the sleek surface of modern cosmology's dearest assumptions. The visual resolution offered by the James Webb Space Telescope lent gravity to the severity of this problem. In contrast to its predecessors, Webb looks through the infrared end of the spectrum, making it possible for it to look beyond the thick gas and dust clouds that shrouded earlier views. It shows galaxies not only as distant smudges, but as structure with visible internal detail. This level of resolution turns theory into confrontation. It compels the scientific community to come to terms with what it really perceives and not with what it has in mind to perceive. That battle is now being fought in research institutions, observatories, and physics departments worldwide. Squads of cosmologists are revisiting the assumptions embedded in their simulations. Particle physicists are asking whether the standard model of fundamental forces must be revised. Astrophysicists are trawling through alternative scenarios, some of which had previously been pushed to the margins, to determine if they could provide explanations now made credible by Webb's remarkable findings. Kaku was also balanced in his optimism. He did admit that not all anomalies result in a revolution, and not all theoretical guessing pans out. But he also told the world something important: science isn't certainty, it is discovery. And sometimes the data isn't lying to us. If we are observing galaxies that conflict with our models, then our models need to get revised. That is how science evolves. He has also opened the discussion to the public, something he has consistently done with elegance and poise. For him, the meanings are not scientific but philosophical. If the universe is older, more complex, and more interdependent than we had thought, what does that imply about human existence within it? Kaku has long believed that science, when deeply comprehended, doesn't reduce our place in the universe, it refines it. In an infinite multiverse of possibility, even the briefest moment of awareness is a remarkable occurrence. With that in mind, he encouraged young scientists and intellectuals to approach this moment not with awe, but with wonder. This might be a generation-defining moment, he declared, the start of a new age of cosmology and physics. Just as the telescope was feared in its time for what it showed, and quantum theory was scoffed at as philosophical rubbish, so too may the current unease herald the dawn of something miraculous. We might be poised on the edge of a new science revolution. The James Webb Space Telescope, he continued, could be more than simply an astronomical instrument. It will also be a philosophical one that not only reveals the stars to us, but causes us to wonder about the nature of reality itself. It might do for 21st century science what Galileo's eyepiece did for the 17th, reveal the universe not as we wanted it to be, but as it actually is. As researchers continue to study the photo, to execute new computer simulations, and to develop the next generation of experiments, Kaku's words reverberate in the background. Anomalies are invitations. They are how the universe gently reminds us that we don't yet know everything. That there is still more to learn. And that maybe, that discovery lies just beyond what we currently believe is possible. In the end, his reaction to the James Webb image was not simply an analysis, it was a call to adventure. A call to leave behind the security of established theory and step into the unknown, guided not by dogma, but by data. To see the cosmos not just as it has been taught to us, but as it reveals itself to those willing to truly look. The universe, he said, does not conform to our expectations. It doesn't owe us clarity. It simply is. And it is up to us to evolve enough to understand it.